Today we're going to take a look at NMR, or nuclear magnetic resonance, which is an instrument that allows the molecular structure of a material to be analyzed by observing and measuring the interaction of nuclear spins when placed in a powerful magnetic field. There are two main types of NMR. Proton NMR, which is used to determine the type and number of hydrogen atoms in a molecule, and carbon NMR, which is used to determine the type of carbon atoms in a molecule. For this video, we will be focusing upon proton NMR, and we're going to observe two structures, proton NMR. First, we're going to look at ethanol, and second, we're going to look at ibuprofen. So the first thing I like to do when I'm setting up an NMR and looking to potentially determine a structure of a particular molecule based off of the proton NMR is set up a chart like I have here. So on the chart, I included ppm, which is the area on the NMR chart that the specific signal will occur. I, which stands for integration, which is the measurement of the area of a particular NMR signal. M, which stands for multiplicity, and that tells us how many hydrogen atoms are immediately next door to the hydrogens produced by a particular peak. And then I have a column for neighbor, which will tell us what the neighbor of the particular peak will be. And then I have a column for guess, which means what part of the structure do I think that NMR peak is attributed to. So first things first is we're going to look at the number of signals. So here we have 3 signals. So this is signal A right here. This is going to be signal B. And this is going to be signal C right here. And if you look and you see these 3H, 2H, 1H, those are indicative of the integration for those particular peaks. So first I'm going to go ahead and start with A, and I'm going to fill out this chart. So if you look at A, the ppm, it can be approximate, so it's probably at about 1.2 ppm. The integration is given to us right here, so for that it is 3H, which means that there are 3 hydrogen atoms in the area of that NMR signal. For the multiplicity, we're going to look at how many peaks are attributed to the signal. So for this one right here, I'm going to zoom in and you're going to see there's 1, 2, 3 peaks. And so for the multiplicity, that will be called a triplet. So I'm just going to write trip for short. And so the neighbor is going to be determined by looking at the multiplicity and subtracting 1 from it. So for example, for this particular signal, the multiplicity is a triplet, so that would mean 3 hydrogens, but instead we're going to go ahead and subtract 1 from that, and you will get CH2, or something with 2 hydrogens next to it. So in order to make the guess for what we think that this part of the structure will be, we're going to look at the integration and the neighbor. So the neighbor of this molecule is going to be CH2. That's already been determined through the multiplicity, and that will be connected to something with 3 hydrogens, as is told to us in the integration. So I'm going to go ahead and say CH3. And I went ahead and drew out the structure of ethanol right up here so that it can be seen because it's a little bit harder to guess the entire structure of a molecule without it being given first. So for the purposes of explaining NMR and proton NMR in this video, I went ahead and drew out the structure so that when we're looking at it, we can be able to attribute the guess to different parts of the structure of the molecule. So in this case, for the part A, we have CH2 connected to a CH3, and that can be seen actually right here in the ethanol molecule. So we are on the right track. So let's go ahead and really quickly do peaks or signals B and C. So signal B is over here. It's at about, 3.6. And the integration is given to us. It's going to be 2H. The multiplicity, I'm going to go ahead and zoom in here, and it looks like we have 1, 2, 3, 4 peaks in this signal. So that is going to be a quartet. So I'm just going to write quart for short. And so as I explained earlier, if the quartet is the multiplicity, we're going to have subtraction of 1 for the neighbor. So for this one, we're going to have CH3. And so the guess is going to be, again, based off the integration in the neighbor. So we will have CH2 connected to a CH3 again. And as we already discussed, that is in the molecule, so we are on the right track. Okay, for number C, or letter C, we are going to see the ppm is at about 3.7 or so. Integration is given to us. It's 1H. So the multiplicity is there's 1 peak, so it's going to be a singlet. I just wrote sing for short. And then the neighbor is subtracting 1 from 1 hydrogen. You're going to have 0 hydrogens. So 0 hydrogens are going to be in the neighbor. And this, plus the signal being more down field for the entirety of the proton NMR spectra, is going to lead us to assume that this can be something like an alcohol, so like an OH, but in general it's going to be something that is attributed to something with only 1 hydrogen and no hydrogens next to that. So I'm going to go ahead and guess an OH for this one. And as we know, in the structure of ethanol, there is an alcohol there. So that is kind of how we're going to set up our chart. And in order to kind of double check, there's this handy dandy NMR table and IR vibrational frequencies table that we can look at right here. So if we go back up to part A, we're going to see that that was at around 1.2 ppm. So we come over here to like 1.2 and we see alkane. And that matches with our guess of CH2 connected to a CH3. So that's perfect. Same thing for the ppm of B. It's going to be an alkane, and that is noted by our guess that we made, and also the integration multiplicity and the neighbor. And then we're going to look at around 3.7 ppm to see what we've got there. So that's around here. And you'll see here there is an alcohol, and that would make perfect sense for what we've done here with this NMR. Now we're going to move on to a little bit of a harder example. So here we have ibuprofen, and we're going to kind of just take it step by step, do the exact same thing. And first things first, we're going to look at the signals. So I'm going to number them or letter them. So I'm going to count this one as A. This is going to be B, C, D, E. These 2 peaks are kind of collective, so I'm going to count both of those together as F. And then this one right here, very far downfield, is G. And I've mentioned downfield once before, but this way is going to be considered to be upfield. And this way on a proton NMR is going to be considered to be downfield. And now what this basically means is it can help to give you a little bit more shed a little bit more light on what is going on in the structure. So in this particular case, we are actually not given the integration, which can make the problem seem a little bit more tricky. So this is kind of going to be crossed out. But once you can tell that these peaks right here are more upfield and these peaks are more downfield, it can actually assist you in figuring out where those molecules are going to be attached to each other. And a general rule is that more protons attached to each other, so more hydrogens attached to each other, are going to be seen at the peaks that are more upfield, so in this direction. Okay, so we're going to go ahead and do our chart, A, B, C, D, E, F, G. And we're going to start over here with G because I think that it's the easiest one. It's at around 11 ppm, which is pretty indicative of an alcohol or a carboxylic acid, something like that, which we've actually just seen. So the multiplicity for this is going to be, it looks like a singlet. So we're going to do singlet. That means the neighbor will not have any hydrogens. So we're going to come down here to our handy dandy chart, look for 11 ppm, and here you will see it's indicative of a carboxylic acid. So for that, we're going to do our guess as an O double bonded to carbon to an alcohol. So carboxylic acid, and if you look at the structure of ibuprofen, right here, you've got a carboxylic acid. So that all works out fine and dandy. Now this right here at letter F is called a doublet of doublets, and what that means is that there are two different sets of doublets together. So I'm just going to write doublet, comma, doublet in my multiplicity section, and if you zoom in really far, you can see that there's 1, 2 peaks here and 1, 2 peaks there. So a doublet of doublet is typically indicative of a benzene ring. So we're going to keep that in mind as our guess. And with these neighboring columns, it can be a little bit hard to determine the neighbor when you do not have the integration on the problem, such as in this one. So I'm going to go ahead and guess that the neighboring will be a carbon to hydrogen and a carbon to hydrogen, and that would be close to a double bond, but just to be sure, and this is at around 7 and 7.2 ppm, we're going to come on down here and look right over here, and here we see aromatic compound connected to a hydrogen, and that is perfectly displayed here in the structure of ibuprofen. Okay, so we're going to go to E now, and they did this little zoomed in thing here so you can kind of see. So you can see that there are going to be 4 signals, so that'll be a quartet, or 4 peaks in the signal, so that'll be a quartet. I'm going to go ahead and say that the guess is going to be something with a CH3 in it, because the neighbor is typically the integration subtracted from 1. So here we've got a CH3, and that is around 4 ppm almost. So I'm going to say 3.9, and we're going to come on down here and look at almost around 4. And if you look, you will see this alcohol peak, and that can be a good indication. We also could potentially, it could be this is technically the same thing, an oxygen binded to a carbon binded to a hydrogen, same thing as this alcohol, but those are pretty much 2 guesses that you could have. Again, it's a little bit hard to guess when you're not given the integration. D is going to be, looks like a doublet. I'm not going to zoom in on that one, but it is a doublet. And then I'll just go through the rest of these. So A is going to also be a doublet. B will be also a doublet, and C is going to be actually a multiplet. So see how there are many, many, many peaks here on C. This is just the blown up version of it. That is indicated as a multiplet. And I'm going to quickly fill in the ppms here. And that just means that there's going to be something attached to multiple hydrogens. Okay, so I filled in the ppms, and the neighbors, I'm going to go ahead and say that these 2 are probably CHs. This one has many hydrogens. And so for our guess, I think it's best to look at this chart and see what we've got. So we've got peak D at 2.5. So if we look right around here, you can see carbonyl compound, that's perfect. So that'll go along with the structure of ibuprofen right here. And then we can also see 2 peaks, or 2 signals, signal C and signal B at 1.9 and 1.7. And if we come on over here, we're going to see again, an alkene, an aromatic compound, which is present. And for this 0.9, remember what I said earlier in that there will be more protons attached to each other the further upfield the peak is. And this signal is also pretty relatively high on the proton NMR for this molecule. So we're going to go ahead and say that is probably this isopropyl group right here, and that can be checked by 0.9 is going to be precisely right here where the alkane category is. So I hope that this video has helped you learn a little bit more about NMR spectral data and how you can utilize proton NMR to confirm the structure of a particular molecule, or even in some instances, guess the structure of a particular molecule. Thank you so much for watching.